Welcome to The Explainer! Today, we're taking a truly fascinating journey to track a deceptively simple thermodynamic principle across thousands of years of human history. We're going to dive into the incredible evolution of evaporative cooling technologies used for food preservation. It's a story that traces this brilliant concept all the way from the sun-baked clay jars of ancient Egyptian and Persian empires straight through to the cutting-edge, machine learning-powered intelligent systems we're building today. It's all about survival, human ingenuity, and how looking backwards might just be the literal key to securing our future.
Right off the bat, let's talk about this staggering number, 30 to 50%. Globally, up to half of all perishable food items are lost post-harvest way before they ever even reach a consumer. That is a massive, critical bottleneck in our global food system, and it disproportionately hits smallholder farmers in low- and middle-income countries who just don't have access to reliable cold chain infrastructure. Without mechanical refrigeration, half of what you spend months growing can literally just rot in the heat.
So, to solve this very modern crisis of food security and energy consumption, we actually need to look to the past. We have to ask ourselves, how did ancient civilizations manage to stay cool and, more importantly, preserve their precious harvests without plugging anything into a wall?
Section 1. Nature's first refrigerator.
To figure out how we get there, we have to start with the basic thermodynamic cheat code that nature gave us. Evaporative cooling isn't just about making things wet. It's entirely about heat transfer. When water turns from a liquid into a gas, when it evaporates, it requires energy. So it pulls that thermal energy or heat right out of the surrounding air and surfaces. The result? The ambient temperature drops significantly. It's an unbelievably efficient, entirely natural way to refrigerate a space. Now, there are two main pathways to harness this process. You've got indirect cooling, where the air is cooled without adding moisture to the primary airstream, and then there's direct cooling, where water evaporates directly into the air, which drops the temperature but does raise the humidity. These fundamental pathways eventually form the absolute foundation for modern air conditioning as we know it today.
Section 2. Ancient cooling masters.
Let's see how ancient civilizations took this basic science and scaled it to create architectural marvels that still blow engineers' minds today. The ancient Egyptians, dating way back to 3000 BCE, were ingeniously using this science through the Mesquites evaporative cooling system. They would strategically stack porous clay vessels filled with water. As the water slowly seeped through the clay, prevailing breezes would cause it to evaporate on the outside. This dissipated the heat and provided a highly effective, completely off-grid refrigeration system for whatever was stored inside. Later on, the Romans took this concept a step further. Instead of just chilling pots, they wanted to chill their entire living environments. So Roman architects integrated evaporative cooling directly into the engineering of grand villas. They used shaded courtyards, carefully placed pools, and strategic cross-ventilation to really harness the breeze. They were essentially building custom microclimates to keep the sweltering Mediterranean heat at bay.
But honestly, the absolute masterclass in ancient cooling has to be the Persian bodgir, or wind catcher. These towering architectural elements were designed to catch the wind and direct it straight down into the building. The true genius, though, is that they often channeled this air over subterranean water channels, known as qanats. The air would cool rapidly through indirect evaporative cooling before flowing up into the basements and living spaces. It was a totally sustainable, energy-efficient method of climate control that worked flawlessly for centuries. Seeing these passive cooling designs fully integrated into traditional architecture is a great reminder that they weren't just functional, they were incredibly beautiful. They harmonized perfectly with their environment rather than fighting against it. Tracing this evolutionary timeline, you can really see the grand sweep of this technology. We started with residential clay pots in Egypt, Mesopotamia around 3000 BCE, moved to the massive Persian wind catchers around 500 BCE, scaled up to huge commercial water cooling towers for factories during the Industrial Revolution in the 1800s, and that brings us straight into our modern digital era, where we're integrating solar power and smart tech.
Section 3. The modern food crisis.
As we arrive in the modern era, we have to recognize that these traditional methods hit a very real ceiling when dealing with our current massive global food and energy constraints. Traditional evaporative cooling is awesome, but it has severe limits. For one, it's completely weather-dependent. If the wind dies down or the air gets too humid, the cooling just stops. It's also static and manual, which simply lacks the precision needed to safely manage large-scale agricultural yields. On the flip side, trying to fix this by just building standard mechanical refrigerators everywhere consumes a massive amount of energy that rural areas simply don't have. So, neither traditional methods nor standard refrigeration alone can save that 30 to 50% of food we are losing today.
So we're faced with a really clear contrast. We need to take the flawless, ancient physics of traditional cooling, which relies entirely on the environment, and inject it with the brains of a modern, adaptive, data-driven network. We essentially need a system that can think for itself. Section 4. Enter intelligent cooling.
This is definitely the most exciting part of this explainer. The era of Intelligent Evaporative Cooling Systems, or IECS. This is where ancient thermodynamics meets cutting-edge artificial intelligence. What the ancient Egyptians achieved by manually pouring water over porous clay, today's engineers are perfecting with machine learning. First, Internet of Things, or IoT, sensors capture real-time climate data, like temperature, humidity, and airflow. Second, machine learning models analyze all this data to predict microclimate shifts. And third, advanced control algorithms autonomously adjust water pumps and fans to optimize the cooling effect in real time. It's an evaporative cooler that literally learns and adapts to its environment.
And you want to know the most astonishing part? The hardware cost for implementing this entire intelligence layer, all the sensors, the microcontrollers, the IoT connectivity, has dropped to under $100. That makes these smart systems highly accessible for off-grid, rural agricultural areas where post-harvest loss is at its worst.
If you're wondering if it actually works in practice, recent research reveals some jaw-dropping performance stats for IECS. We're seeing average temperature reductions of 11.2 degrees Celsius. We are seeing energy savings of 75 to 90% compared to standard mechanical refrigeration. But most importantly, it's extending the shelf life of perishables by up to 200%. And because the whole system is so cheap to build and run, the payback period for a farmer is just 1.2 years. It is an absolute game changer.
Section 5. The future of preservation.
As we look forward, the big question becomes, how do we take these highly effective, low-cost systems and scale them globally? The research tells us we still have a few gaps to close. First, we need to validate performance in wet, humid climates where traditional evaporation normally struggles. Second, we have to standardize the agricultural IoT protocols so different systems can actually talk to each other. And finally, we need to build explainable AI. Farmers really need to trust the system, which means they have to understand exactly why the AI is making the decisions it's making regarding their valuable crops.
But a new 4-tier framework for next-generation systems is paving the way for the future. Researchers are developing desiccant-enhanced materials to strip humidity right out of the air, which allows evaporative cooling to work even in the tropics. Combine that with renewable solar energy, AI-integrated adaptive controls, and advanced interstage humidification, and we have a system that can perfectly optimize agricultural storage entirely off the grid.
Which leaves us with this final, provocative thought. As we face mounting pressures on our global food supply and our fragile energy grids, we so often look to invent something entirely new. But by taking the time to supercharge ancient wisdom with modern artificial intelligence, we might just have uncovered the exact blueprint we need to solve tomorrow's crises. Thanks for joining me on this explainer, and I hope this sparks you to look at the intersection of history and technology in a whole new light.